Welcome to this podcast brought to you by the Vatican Observatory Foundation. I'm your host, Bob Tremblay. I'm a volunteer NASA JPL Solar System Ambassador, first Vice President of the Warren Astronomical Society in Michigan, and factotum for the Vatican Observatory Foundation. For this podcast, we're going to do things a little differently. Sacred Space Astronomy is our online community of friends of the Vatican Observatory. We have several astronomers and scholars who write articles about astronomy, space science, and faith and science. Every full moon, the Vatican Observatory hosts a Zoom meetup for our Sacred Space Astronomy subscribers. Typically, our guest will be a member of the Vatican Observatory staff or an affiliated researcher, and they'll tell us about the research they're doing and the journey that led them to the Vatican Observatory. Br Guy Consolmagno, director of the Vatican Observatory and president of the Vatican Observatory Foundation, usually acts as host during these meetups. This podcast is taken from the full moon Zoom session that was recorded on January 28th, 2021. Our guest was Dr. Michelle Francl, professor of chemistry at Bryn College in Pennsylvania and an adjunct scholar at the Vatican Observatory.
Well, it's nice to be here. I'm a professor of chemistry at Bryn College, which is a small college for women outside of Philadelphia. And as Guy mentioned, I've also been an adjunct scholar at the Vatican Observatory, I think since 2015, something like that, maybe the last 5 or 6 years, which has expanded my network of people I can talk to about science to include more astrophysicists, which has been great. I'm a theoretical chemist, and the kinds of things I'm interested in are methods developments for quantum mechanics, which nobody wants to hear about, not even most chemists. But I'm also interested in weird molecules, molecules that don't behave the way chemists expect them to. And molecules in interstellar space are some weird molecules occasionally. And so that there's cross interests there for me. So that's maybe what I do in a nutshell. I also write. So I write a regular column for Nature Chemistry about science and policy and history and philosophy of chemistry. And then sometimes I change hats and change names entirely and write about Catholic spirituality. So I just finished a book on prayer this fall, writing under it's not a pseudonym, it's just another name.
Well, I'm going to get back to the science because I've heard you give some talks on these molecules and I think they're fascinating. So we're definitely going to get there. But before we get to the good stuff, tell us a little bit about your background. Where did you grow up? What was your family like? And how did you get into science?
So I am the oldest of 6 kids. I was born when my parents were graduate students at Tulane in chemistry. So I spent my formative year in the womb in an organic chemistry lab, which may explain a lot. I'm the oldest of 6 kids. I grew up in a very small town outside of Chicago. There were like 2,500 people in the entire town. I went to the little Catholic school there, which there were 13 people in my combined 7th and 8th grade. So small, small, small. But the sisters there, the ladies of Loreto, were intellectually incredibly curious and happy to kind of fuel my interest in science fiction. So that's when I started reading science fiction, and I can really thank the sisters for encouraging me to read broadly. And we moved to California when I started high school. My high school had 4,000 students in it. I didn't talk to anyone for a year. It was a little bit of a culture shock. But Huntington Beach, California was beautiful. The weather was great. I went to UCI, University of California, Irvine. It's the local University of California campus, and decided to major in chemistry and linguistics.
So you stayed there for your PhD?
I stayed for my PhD because I married one of the graduate students there, and I switched from being a synthetic chemist to being a theoretical chemist. I got totally captivated by quantum mechanics, and computational chemistry was just beginning to take off. So it was a really exciting time to be involved with that, and very few places in the US doing it. Irvine was one of them. I was really lucky to get to work for Sherwood Roland, who at that time was working on the ozone controversy, and I collaborated with him and his group on some calculations on small molecules in the atmosphere. But Sherry was, again, somebody who was excited about science and excited about how that intersected with culture and politics and society, and just generally a nice guy. So that was a good introduction to kind of the broader world of science for me.
Was he a Nobel laureate or?
Yep, he won the Nobel Prize along with Mario Molina, and someone whose name is escaping me, for figuring out exactly the processes involved in the decomposition of ozone in the stratosphere. So
Very cool. Now, by computational chemistry, you're not just talking about working out chemical equilibrium calculations.
no, so I'm thinking about using the Schrodinger equation and those differential equations that stem from that to solve the Schrodinger equation to get the energy. And if you have an energy surface, it turns out that's an entree into figuring out the structure of molecules. And so it gives me methods for finding the thermodynamics, like how much energy it takes to turn one molecule into another, or how fast a reaction goes by figuring out how much energy you have to kind of push in to boost it over a hump, or to figure out the structures of molecules that people haven't yet done in the lab. So fun things to do is to, propose a molecular structure, have somebody synthesize it, and then see how close the structure they get is to the structure I predicted.
So you've continued working in this corner ever since. You've done some really weird molecules.
I have done some really weird molecules. The current interests around molecules that are topologically weird. So I'm really interested in these Möbius strip molecules that have just one side to them. So if you, stick your finger on one side of the molecule and slide it around, you'll come back and then sort of go inside the molecule. But they're very elegant. And the reason that chemists are interested in these is because they're chiral. They're mirror images of each other. And biological systems are inherently chiral.
So if I can remember from the talk I saw you give, imagine a benzene ring only with more than 6 molecules.
Yeah.
And then imagine a second benzene ring and then connections between the 2 rings. And then you've got a ringed molecule. And then you twist that ring so that the upper ring connects to the lower ring and the lower ring connects to the upper ring. Have I got that? Now, are these real molecules or are these theoretical molecules?
Oh, these are kind of theoretical molecules. People have made molecules that aren't quite as beautifully symmetric as these. These turn out to be hard to make because they're pretty insoluble, and the easiest way for chemists to make molecules is in solution. They probably do exist in smoke. So it turns out you can isolate lots of really strange molecules from smoke and identify them. None of these have been identified, but very similar molecules with oxygen atoms in them have been made. The oxygen atoms just turn out to make them more soluble, so that's part of it. They're not as pretty as my molecules, I have to say.
And what does this get you? What do you learn from these?
So one of the things you learn from these are about what kinds of constraints come into play in making these molecules as strained as they are. So these are really what we would call high energy molecules. So you can sort of see they have a barrel along the back and then one spot where that twist is embedded. And to chemists, that's a weird thing because you would think that the strain would want to distribute itself kind of around the molecule rather than collecting in one place. So this means this is a way to make high energy molecules and store energy. So fuels. So these things are related to fuels and also to rocket fuels. So high energy materials are associated with things that you could put into a rocket or use as not quite a battery, but as a way to keep energy until you're ready to release it. The other interesting thing about these molecules is because of the twist, they have this handedness. And biologists know that life is handed. If you want to make new molecules, you want to make molecules of a particular handedness, either right-handed or left-handed, because they'll have very different biological activity. And my general example for this is spearmint and caraway, which are exactly the same molecule, just mirror images of each other. But you would never confuse the taste of spearmint with the taste of caraway seed.
That's bizarre.
It is totally, I mean, I find that the tastes of those are so different, yet they are exactly the same molecule, just one is a mirror image of the other, but it tells you how good we are as biological systems in discriminating between those images.
Well, since you've mentioned taste, I have to jump to a completely different
I
chemical
know what you're
topic.
going to ask.
How
Yes,
did you learn the taste of heavy water?
I drank it.
There's got to be a story behind that.
Of course, there's a story behind that. So the story began with my students who wanted to know if you could make tea out of heavy water and would that poison somebody? And I,
Describe what heavy water is to anybody in this who
ah,
wouldn't know.
right. So heavy water is regular water, but instead of the two hydrogen atoms on it, uh, water kind of looks to a chemist like Mickey Mouse. It's got an oxygen atom and two little ears that come off of it. And the two ears are the hydrogen atoms. And if you replace those hydrogen atoms with deuterium atoms, which are just hydrogen, except they weigh twice as much, hence the word heavy water. Deuterium is an isotope of hydrogen. One of the things about isotopes is chemically they tend to behave the same as their parent atom, but you can detect them by weight. So the story involves three Nobel laureates, one of them Catholic, one of them Harold Urey, one of them a very disgruntled Lawrence, and several goldfish and a mouse. So here we go. So my students asked about drinking heavy water. I said I would see what I could find. I discovered that there's a rich literature about heavy water and drinking it. And it began with Harold Urey, who isolated deuterium and had, source of heavy water. And he shared it with George de Hevesy. George de Hevesy won the Nobel Prize for radio tracing, for isotopic tracing. And he had wondered about how you could track water moving through the body. And the way to do that was using deuterium. And Harold Urey sent him 2 liters of deuterium. And he began by taking some of that deuterium, some of that heavy water. There wasn't much deuterium in this heavy water, I'm going to say. It was only 0.5% enriched. But they put a bunch of goldfish into the water, and then they let them sit in there for about a day. And then they fished them out of the water and weighed them. And they weighed more, and the water weighed less, which meant that they had taken up some of that D2O into the goldfish. So then they put the goldfish into regular water, let them sit there for a day, took the goldfish out. Now the goldfish weigh less and the water makes war. So we're always exchanging water with the system. So then they decided, well, nothing bad seemed to happen to the goldfish. I mean, that's what they say in their Nature paper. The goldfish seemed unworried by all the heavy water that they were imbibing. So they decided to drink it. And he and his assistant drank 2 liters of deuterated water, pretty much the entire sample that Urey had sent them, and then tracked the water by isolating it from their urine. So they distilled, I don't know, 400 times their urine in order to figure out how fast the water moved through the body, which was the first measurement that had been made of that. So it was kind of interesting. So they drank it without any difficulty. About a year later, this guy in Norway was like, I'm going to drink heavy water and it's going to be a media event. And I'm going to do it in front of the, photographers, and they're going to have resuscitation equipment because Lord knows what will happen to me if I drink it. But he seems unaware that de Hevesy and Hofer had drunk it without any difficulty. So he drinks it and he says there's a terrible burning sensation when he drinks it. He drinks about a teaspoonful. I will point out that that teaspoonful probably cost in current dollars about $100,000. This was a very expensive stunt. And Urey was like, that's ridiculous. He thinks it should taste the same because the thought about isotopes is they don't really change the chemical properties, which would include taste. So Urey then held at Columbia University a big public tasting, and he and a colleague did blind tastes of a milliliter of pure D2O and water. And they claimed not to be able to taste anything at all. And then there was this guy in England who said it tastes sweet. And that's really weird. I mean, chemists know what makes things taste sweet, and water should not taste sweet. Tasting heavy water still seemed like something I wasn't sure I really wanted to do. So I reported back to my students, we had a nice chat, and I ordered a little thing of D2O, and it sat on my desk for about 6 months before I got brave enough to open it and try it. And I ordered 10 mils of it. It costs now about a liter bottle of D2O is about $1,500. So it's still a pricey experiment, but I didn't order a liter. I ordered 10 milliliters. I brought in my mother-in-law's very fancy little crystal glasses. For something that expensive, we got to have fancy glasses. And one of my students helped me do a blind tasting. So they filled distilled deionized water in one glass and the D2O in another. I came into the room, I tasted it, and D2O tastes sweet. It's 100%. It's as sweet as the cup of tea I'm drinking, which is totally weird. Also, nothing bad happened. And I did mine, you know, with that. I recorded it. It's on YouTube. You can watch me drink it on YouTube. Because, you know, if you're going to do this, you should prove it. But then it turns out when I put that up on YouTube, I got contacted by a group of scientists, but who figured out why D2O tastes sweet. And it has to do with binding to a particular protein. And so they've done some really cool experiments to suss this out. So it's been kind of fun to follow that research. So that was kind of a, you know, a weird sideline. But the mouse part of the story is that Gilbert Lewis at Berkeley fed a bunch of D2O to a mouse, but he told Lawrence, he was trying to get Lawrence, who would eventually get another Nobel Prize, to come to Berkeley, and he told him, oh, you can have this this heavy water to experiment with. But Lewis gave it to the mouse instead, and Lawrence was really angry that he'd wasted the water, you know, on a rodent.
Of course, the other place where I've encountered sweet water is at the very end of The Voyage of the Dawn Treader, the Narnia book. So where you have a rodent drinking water.
I had not made that connection till now. Yes, there we go. Next time I talk about this, I can add that piece.
So what was your path then from UC Irvine to the East Coast?
So I went to postdoc at Princeton, still doing computational chemistry work, really then kind of solidly centered around methods development and not so much around molecular structure. And from there got the job at Bryn, where I have now been for 35 years, which feels like, you know, forever and a day, and not very long at all.
And so if I can ask a very personal story, but of course something very tragic happened while you were just arrived at Bryn Mawr.
Yeah, that, you know, so that's the sad part of the story. So the reason that I came to Princeton to postdoc is because as I said, I married another graduate student, and we looked for jobs that were together. And we found 2 jobs in New Jersey. So we moved from California to New Jersey. And the sad thing is the first year at Bryn Mawr, Tom passed away. And so that made, you know, the start to my career at Bryn Mawr pretty tough. The institution was incredibly supportive. I have to say, my mother wanted to take me home, but the college president assured her they would, you know, watch out for me, and they did. So that was, there was quite an introduction to the way a small college can work.
So you were a widow in your late 20s.
I was a widow at 29, which is just not a thing. The flip side to the story, though, is that after 7 years at Bryn Mawr, they hired a mathematician. The math department chair at the time said she hired the mathematician because she's an inveterate matchmaker. And I eventually married the mathematician, and we have 2 fine sons. So
fabulous.
It definitely was, you know, a happy ending to, you know, to a difficult moment.
Well, the other thing that occurred during that time, if I understand right, is you developed another academic interest besides chemistry.
Oh yeah, so what do academics do when they have a problem? They read and they research and they do a literature research. So I was trying to figure out how to deal with the problem of evil in the world. Why did God let bad things happen? So I went and worked on a degree in theology at the local Catholic seminary. Um,
So
so
you have an all but thesis degree in
I
ABT?
have an all but thesis degree. And at this point, I probably could take a bunch of the things I've written, staple them together, and make a case that I, would like the actual degree. But, it's not really the degree I was going for. It was more, the curated reading list that those kind of graduate courses give you.
How did that lead to your writing career?
So funny thing that, so the reason I'm ABD is because I eventually had 2 kids, and having a full-time faculty position and 2 small children was just not compatible with finishing that degree. And so I didn't do any writing in theology for some time. And then we'd been at a party and somebody made a comment about that movie Into Great Silence, which followed a year at a Carthusian monastery. And somebody made some comment about I couldn't be silent that long. And I said, oh, I go, regularly on, 8-day silent retreats. And they were sort of taken aback. So I ended up writing an op-ed for the Philadelphia Inquirer, which got published on the joys of silence. And then I got an email, and the name on the email said Bishop. And I have a colleague named Mark Bishop. So I assumed it was from Mark Bishop. It was not from Mark Bishop. It was from the Bishop of Philadelphia, who said, if you can write for them, you can write for us, and invited me to write for the local Catholic paper. So that kind of jump started that as a second career. By that point, my kids were in middle school. The bishop had taught me systematic theology. So it wasn't a total out of the blue request. And he knew that I could write beyond the op-ed. So I wrote for almost 5 years for the local Catholic paper.
One of the things that you do is you write up cool stories like this for Nature. How did that happen?
So that happened because I've been keeping a blog, and the blog started with stuff from, well, started partly with an NSF grant, but mostly it had to do with the kind of odd questions students would ask me, and that weren't really part of the lecture. So I didn't want to spend lecture time on them, but still were kind of interest. So I started something called Culture of Chemistry for them. And would post stories like that. The editor for Nature Chemistry read it and got intrigued and invited me to write a couple of short essays for them because they were launching a new journal, Nature Chemistry. And I did, and they liked them so much they've been for the last decade asking me to write them for a year. So I'm about to send them my 50th.
What of all of those different articles that you've written has drawn the most attention?
The heavy water actually one has drawn a fair amount of attention. The one I wrote about Marie Curie got a lot of attention about the built space that scientists use. And then there was one that I wrote about temperature and the measurement of temperature, and how that really shifted chemistry into a real science. That may be the moment when chemistry pitched from alchemy into the sciences.
I've got to go back to this Marie Curie and built space. What do you mean by that? That's very intriguing.
So, how do we build laboratories, and do we make laboratories? So I teach at a women's institution. Women are generally shorter than men. Lab benches are designed for men to work at. So when we designed a new lab, we designed one that would fit the average student at Bryn Mawr. So the benches are lower, and we have adjustable power strips that come down from the ceiling so that if you're tall, it's convenient for you, but also convenient for me, who is not tall, to be able to get at things. Things were put within reach. We also send a lot of signals with color around things. So we color code stuff blue. Blue is for boys these days. And so there are some kind of interesting things about how we construct space to make it less convenient for women. So, you know, if you add up all the time that women spend climbing on ladders to get stuff down, that turns out to be significant. So to think about, you know, how do we design spaces that are perhaps more universally accessible? The sidelight to this and what we've done at the college is that these labs are now accessible to people in wheelchairs. And so we've had students who are in wheelchairs or otherwise mobility impaired, blind students who can now use the laboratories more effectively. So in some ways, it's a little bit about human dignity and social justice. But that one got a lot of attention as people think about how do you design spaces for that give access to the most number of people to not restrict people's ability to do science.
Tell a little bit more about the thermometer story then.
So it turns out that figuring out how to measure temperature was a long path. So, you know, you asked everybody, you know, what was the temperature today? And we gave it on different scales, Celsius or Fahrenheit, but it was a long path here. And I'm going to say you inadvertently started this, this particular essay, because when I visited once in Rome, we were going on to Florence and you suggested we go to the Galileo Museum. And it was a cold and rainy day in Florence. So we went to the Galileo Museum, which has this huge display of beautiful thermometers, blown glass thermometers, and a little bit about the history of the measurement of temperature. And it used to be that originally when people wanted to run an experiment, so lots of experiments, the temperature matters a lot. You change the temperature a little bit, the reaction goes much faster, much slower. So if you want to repeat it, you need to repeat it at the same temperature. And it used to be you literally marked something on a little tube and packed it carefully and shipped it to somebody who would then use the same thermometer. There wasn't this notion of the scale on the thermometer. And figuring out, you know, how do you pinpoint a thermometer? What sorts of mixtures would you use so that you and I both know when we calibrate our thermometer that they're calibrated in the same way? There's a beautiful book by Chasuk, who's at Harvard, about the development of the thermometer. It has a Jesuit twist to it because the scaling of the thermometer was originally proposed in a book of mathematical exercises written by a Jesuit whose name is escaping me.
I know that you teach more than just chemistry there. You also have this team taught course that in the past has brought students to Japan and other interesting places. Can you tell us a little about that?
Yeah, that's a little kind of a crazy thing and that has to do because I had all that work in theology and because I've been writing about contemplative practices and mysticism in various ways. And one of my colleagues in psychology stumbled across that, and he wanted to teach this set of courses on meditation and contemplative practices. And he had someone to talk about the Buddhist end of things, but not something to talk about the Western end of things, kind of the Judeo-Christian tradition. So he ran into me. It's another one of these, you know, you run into somebody on a bus or in a line. We were in line to get our flu shot. And he says, so I have a proposal for you. So we ended up teaching this class 3 times. We take students to Jesuit retreat houses, to small monasteries up here in Connecticut. There's a women's monastery we've been to see hermits in Japan, Christian hermits in Japan, to stay in Buddhist monasteries in Japan. It's been quite a fascinating course to teach.
To try to crystallize the main idea that you're getting across to your students, that you're learning yourself teaching it, what would that be?
That would be that the silent spaces and the ability to listen to the universe, whether you see God in that universe or not, is a human thing. And that many traditions have some way of kind of institutionalizing that or helping to frame it, to think about, you know, how do you listen to the sort of ineffable voices around you? And whether, you know, that's within creation or whether that's within, you know, as it would be for me, for thinking about, you know, listening to God. But how do we listen? might be the real take-home message.
Does that feed into the way you do your science?
I would say it does. That part of what I do is listen to those molecules and try to see what they're telling me, as opposed to putting my own thoughts on how they should behave. I'm really most interested in molecules that behave in ways that surprise me, or surprise chemists as a whole. And to do that, you have to be willing to see what's there and not what you want to be there, what you wish were there, but what actually is there. So I think the two are not unrelated to each other.
So, and since we're coming to the last couple of minutes, if people have questions, feel free to type them into the chat. But I'll ask a question that I get asked. As a scientist, what is your most cited paper and what is the paper you're most proud of? Because usually they're not the same.
Correct. They are not the same. They are not the same for me. My most cited paper is a methods development paper in quantum mechanics, the 631G star basis set, which is used widely in calculations by chemists and physicists these days, and gets cited, I don't know, a dozen times a week, which is kind of crazy. But the paper that I am perhaps proudest of is one that was a collaboration with a synthetic scientist, and we were trying to understand the ways in which that molecule, again, has a surprising structure, and to sort of get under its hood and figure it out. And I proposed molecules they could synthesize. It took them almost a year to make the molecules. And then we got on the phone together and he sort of opened up the envelope and says, "You're right." But it was such a great collaboration and such a great test kind of the methodology.
Do you feel the same kind of joy when that happens that you would do in, a moment of prayer, a moment in a retreat? Do you see that connection?
Yeah, because in a way it's like, it's like having a conversation with God. I ask a question about the molecule, and I mean, God made all the rules about those molecules, right? Surprising and otherwise. And so, it's sort of like my saying to God, "Is this how it works?" And God saying, "Yeah, that's kind of how it works. And let me show you something else." I mean, to me, it feels very conversational, and an ongoing conversation. And, that's another way of thinking about prayer, as an ongoing conversation with God.
That's a wrap for this podcast. Our audio editors were Br Guy Consolmagno and myself, Bob Tremblay. You can listen to our other podcasts and read articles from us on our website at vaticanobservatory.org. Clear skies, everyone.